For this problem, we have a computer disk starting from rest and speeding up with an angular acceleration of 190 radians per second squared till it reaches a speed of 7,200 RPMs, which stands for rotations per minute. So let's go ahead and set up our angular kinematics for this one. We know we're starting from rest. We know our angular acceleration is 190 radians per second squared. And we know our final speed is 7,200 RPMs, but we need to go ahead and convert that number because we don't want it in rotations per minute. We want it in radians per second. So 1 minute is going to be 60 seconds, and we know that one rotation is going to be 2 pi radians. And so we end up getting an angular speed here of 754 radians per second. So we can go ahead and use that number to solve for our angular displacement here. I'm going to use this equation. 754 squared equals 2 times my angular acceleration, 190, times my angular displacement. And so I end up getting an angular displacement here of 1,496 radians. Now, it asks how many revolutions it makes after 10 seconds. So we don't really know how long that's going to take, and this is a little bit tricky with this problem, but let's see how long it takes to speed up to a speed of 754 radians per second. And so we could say 754 is going to be equal to our angular acceleration 190 times t, and so we find that our time to speed up is 3.97 seconds. So this does not represent the entire time. So we need to now think about a second kinematics chart here and think about its motion once it reaches that speed. Okay, it's going to be moving at a constant speed, and so we need to figure out how far it goes during that time. So we're moving at a speed of 754 radians per second. That's both our initial and final since it's constant. Our acceleration is 0, and our time that we're moving at that speed is going to be 10 minus 3.97, or 6.03 seconds, the remaining time. So we can go ahead and find our angular displacement for that time. I'm just going to use omega initial t plus 1/2 alpha t squared, and that second term, of course, goes away. And so I get that my angular displacement here is going to be 754 times 6.03, which gives me a displacement of 4,546 radians. Now for the final step here, I'm going to take these two angular displacements and I'm going to combine them. So we have 1,496 plus 4,546, giving me a total angular displacement of 6,042 radians, but we want it in revolutions, so we need to convert back here, knowing that 2 pi radians is 1 rotation or 1 revolution. So we end up getting a final answer here of 962 rotations, or 962 revolutions. For this problem, we have an angular motion graph, and in this case, it's a position versus time graph, so we do want to keep that in mind. And what it's asking is, what is the angular displacement of the wheel between 5 seconds and 15? In order to get that from a position graph, we're simply going to read the graph. So we look at 5 seconds, we're at 100. At 15, we're at an angular position of 125 radians. So that means our displacement, our change, is just going to be 25 radians because we go from 100 here to 125. For the second part, what is the angular velocity of the wheel at 15 seconds? What I'm going to be thinking about is the fact that the slope represents my angular velocity in this case. So I'm going to pick some points up here on my graph. So I have the point 10, 150, and I have the point here, which is 20, 100. And so the slope of this line segment here, all right, we have a constant velocity during that period of time, and the slope of that is going to be the angular velocity at every time between 10 and 20 seconds. So I'm going to say that my angular speed is just going to be delta y over delta x. So that's going to be 100 minus 150 over 20 minus 10. So I end up getting an angular speed here of -5 radians per second. If we want to round this to 2 sig figs, it would just be -5.0. So for this first one, we have a horse on a carousel rotating around at a rate of 0.14 revolutions per second. We want to know how long it takes the horse to go around twice. Okay, I'm going to show you how to do this using angular kinematics, although you probably can reason your way through this. So with angular kinematics, we're going to say the carousel is rotating at a constant rate here, and it's rotating around twice, so 2 times 2 pi, or 12.57 radians. That's 2 revolutions. And then we're going to go ahead and figure out this angular speed here in radians per second, because it's in revolutions per second right now. So 0.14 revolutions per second. We don't need to convert the seconds, but we do need to convert the revolutions into radians. So there's 2 pi radians in 1 revolution, and so we get an angular speed here, which will be both initial and final, of 0.88 radians per second. And so we can now use this setup that we have here to solve for the time. So I'm going to go ahead and use my delta theta equals omega initial t plus 1/2 alpha t squared. That second term goes away because our angular acceleration is 0. And so I get 12.57. It's going to be equal to 0.88 t. When I go ahead and solve for the time here, I end up getting that my time is going to be 14.3 seconds. Rounded to 2 sig figs, it would just be 14 seconds. For my second part, I want to know how fast the child is going in meters per second. So this is really looking for the tangential velocity of a person on this horse. And so I can get that tangential velocity from my angular velocity by just doing r, my radius, times my angular speed. I do need to make sure for this problem that I do this angular speed in radians per second, otherwise I will not get my tangential velocity in meters per second. So, knowing that my radius is 3.6 and my angular speed is 0.88, I just multiply those two together and I get an angular speed of 3.16 meters per second. Rounded to 2 sig figs, it's just 3.2 meters per second. Alright, for this problem, we have a car speeding up from rest, and we want to know how many times each tire rotates while speeding up. So in this situation, I'm actually given a lot of information about my linear or translational kinematics here, so I'm just going to start with that, just like an old problem. So I'm going to say my initial velocity is 0, my final is 20 meters per second, and my time here is 14 seconds. And then I'll worry about getting this over into angular quantities later. So I'm going to start with my delta x equals 1/2 Vf plus Vi times t. So my linear displacement is going to be 1/2 times 20 plus 0 multiplied by my time of 14 seconds. And so I get a linear displacement here of 140 meters. Now, I can link that linear displacement to the angular displacement of the tire. Okay, so I know that my diameter here is 58 centimeters, which means my radius is going to be half of that, 58 over 2, or 29 centimeters. And I'm, of course, going to convert that into meters, so 0.29 meters. So that's going to be the radius I use. And I'm going to use that in the equation delta x equals r delta theta. So I know my linear displacement is 140, my radius is 0.29, and so I can solve for my angular displacement. So I end up getting an angular displacement here of 483 radians. Okay. I want it ultimately, though, in rotations because it says how many times did each tire rotate. So I'm going to convert that 483 radians into rotations, so 2 pi radians in 1 rotation. And so I end up getting an angular displacement here of 76.8 rotations, rounded to 2 sig figs. It's just going to be 77 rotations. For this next problem, we have a variety of forces acting on a disk. And we want to go ahead and find the net torque on the disk because of the forces. So I'm going to go ahead and number these forces here, 1, 2, 3, and 4, and I'm going to find the torque from each one. So each time we're going to be using the fact that torque is RF sine of theta. Okay, and so for this first one, my radius, it's going to be the entire radius of the disk because that force is on the edge. And so we know the diameter is 12, which means the radius is 6 centimeters or 0.06 meters, half that diameter, and then just convert it into meters. And so I end up getting, for the first one, the torque is going to be 0.06 times my force, which is 30, and my angle here is going to be a 90-degree angle between the radius here, r, and the force. And so that's just going to end up being 1 here, and so I get a torque from force 1, which is going to be equal to 1.8 Newton meters. Moving on to the next one, torque 2 here, same thing. We're doing torque equals RF sine of theta. My radius for this one is going to be 0.05, this distance here shown on the graph, or on the diagram, times my force, which is 20, and it's going to be sine of 90 once again, because the angle between my force and my radial distance is 90 degrees. And so I get that this torque is going to be equal to 1 Newton meter. Continuing on with torque 3 here, I'm once again going to do RF sine of theta. And so the torque from that one is going to be the radius, which is 0.05, the distance from the pivot to where that force acts, times the force, which is 30. And here I do actually have an angle. It's given as 45 degrees, that angle between the radial distance and the force. And so I end up getting a torque here of 1.06 Newton meters. And for my final torque, it's going to be the torque from that 20 Newton on the edge there. And I could do RF sine theta and go ahead and solve for this, or I could realize that that force and that R have an angle of either 0 or 180, depending on how you're looking at it. And so the torque from that one is just going to be 0. I'm now going to go ahead and think about my directions and then add them up to get my net torque. So object 1, or torque 1 here, that's going to cause a clockwise rotation, which means this one here is going to be negative. Torque 2 is going to cause a counterclockwise rotation, which means that that's going to be a positive torque. And torque 3 is also going to cause a counterclockwise rotation, making that one positive as well. So the net torque, or the sum of my torques, I'm just going to add up the 3 that I have, so negative 1.8 plus 1 plus 1.06, and end up getting a net torque here of 0.26 Newton meters, and it would be in the counterclockwise direction. For this one, I have 2 forces acting on an object, and I want to calculate the net torque about this pivot point here, which is indicated by that dot. And so I'm going to set up the torque from each one. So each time we're going to do torque equals RF sine of theta. So my radial distance here is going to just be this distance from the pivot to where the force acts, which is 0.75 meters. My force is going to be 13 newtons, okay? And my angle here is going to be 90, because that's the angle between R and F. And so I end up getting a torque from this one of 9.75 Newton meters. For the second object, all right, the second force, I could go ahead and set this up, but what I'm going to end up finding is that the torque and the radial distance here are in the exact same direction, so my angle is either 0 or 180. Either way, the torque from that ends up being 0 Newton meters. So my net torque is just the torque from this first force, the 13 Newton force. Rounded to 2 sig figs, it would be 9.8 Newton meters. Alright, so we have a problem here with a toy top with a diameter of 5.4 centimeters, so that means the radius here is 2.7 centimeters, and it has a moment of inertia of 2.8 times 10 to the negative 5th kilogram meters squared. And we're going to exert a force on the end of it, a force of 0.25 newtons, to make it begin to spin. We want to know how long it's going to take to complete the first 5 revolutions. So I basically started here with my free body diagram. I'm going to think about what torques I have acting about this pivot point. And the only torque I'm going to have is from this pulling force. So I'm going to call that the torque of the pull. Now that we have that, we can go ahead and set up our sum of the torques equals I alpha. And there might be a few other things we need to do, but this right here is our main equation that we have to go through. So the only torque I have acting on it is the torque of the pull. That's going to be equal to I times my angular acceleration. I can substitute in R times the pulling force times sine of 90 for that torque of the pull. That's going to be equal to my moment of inertia, which is 2.8 times 10 to the negative 5th times alpha. So I can go ahead now and substitute in the radius, which is going to be 2.7 centimeters, or 0.027 meters. The force is 0.25, and the angle here is going to be sine of 90. It doesn't specify. It's technically perpendicular, but otherwise we can't solve the problem, and that's a fair assumption to make, I think, in this case. So that's going to be equal to 2.8 times 10 to the negative fifth times alpha. So I get an angular acceleration here of 241 radians per second squared. Now that I have my angular acceleration, I can go ahead and set up my angular kinematics. So I know my initial angular speed is 0. It's starting from rest. I'm worried about how long it takes to go 5 revolutions, so that's going to be 5 revolutions, but we want to convert that. We know 1 revolution is 2 pi radians, and so we get 31.4 radians for my angular displacement, and I know that my angular acceleration is this 241 radians per second squared. Okay, so I can set up delta theta equals omega initial t plus 1/2 alpha t squared. That initial term goes away because I'm starting from rest. I end up getting 31.4 equals 1/2 times 241 times t squared. So my time here that I end up getting when I solve for that is 0.51 seconds. Moving on to this next one, we have a 12 centimeter disc that's speeding up to a speed of 2,300 rotations per minute. Remember, that's what RPM stands for. And we want to go ahead and figure out how much torque is applied to this disc to allow it to speed up. So of course we're going to do sum of the torques equals I alpha. We're looking for that net torque, so I'm just going to leave that as sum of the torques on that left-hand side. My moment of inertia, I know it's 2.5 times 10 to the negative fifth, but I don't know my angular acceleration. So I need to go ahead and find that first in order to be able to find the net torque. So in order to do that, I'm going to think about angular kinematics here. I know I'm starting from rest, so the initial speed is 0. I know the time it takes is 3 seconds, and I can figure out that final angular speed. I'm just going to need to convert a little bit. So I have 2,300 rotations per minute, and we want to convert that to radians per second. So I know that 1 minute is going to be 60 seconds. And I know that 1 rotation is going to be 2 pi radians. And so I find that the angular speed in radians per second is 240.9 radians per second. So I can substitute that in here, or put that in here for my final angular speed. And then I can go ahead and get my angular acceleration. So I'm going to use omega final equals omega initial plus alpha t. So 240.9 equals 0 plus my angular acceleration times 3. So I get an angular acceleration here of 80.29 radians per second squared. Now that I have that, I can go ahead and substitute that into my sum of the torques equals I alpha equation. So this is 80.29, and I end up getting a net torque here of 0.002 Newton meters. If I wanted to make that to 2 sig figs, it would be 0.0020 Newton meters, or 2.0 times 10 to the negative third Newton meters. Either one would be acceptable there. For the second part, I want to know how many revolutions does it make before reaching full speed. So I'm going to use my angular kinematic setup once again, and I'm just going to solve for delta theta using this equation here. I really could use any equation, but I'm going to use this one here. And so I get that delta theta is 1/2 times my final angular speed, 240.9, times my time, which is 3. So I end up getting an angular displacement of 361.2 radians. But we need to convert that, so 2 pi radians is 1 rotation. And so my angular displacement in rotations is 57.5 rotations. Rounded to 2 sig figs here, that just is going to become 58. So let's go ahead and get started with this problem here. We have a situation where there's a combination of linear and angular quantities. So what we're going to want to do is set up all the forces acting on any object that's accelerating and all the torques acting on any object that's undergoing an angular acceleration. So we'll start with this box here that's hanging, that's 1.5 kilograms. We have the force of gravity acting on it, of course, as well as the force of tension because it's connected to a rope there. And on the pulley itself, we're going to have the force of tension, the same force of tension that exists on this box because it's the same segment of rope. And we have this 10 Newton force here as well. We're also going to have the force of gravity and some force from the axle here, but those aren't really going to be relevant because we're going to have a torque only from these two forces. So I'm going to fill that in as well, just to indicate that we have a torque from tension going that way and a torque from this 10 Newton pulling force going the opposite way. Now that I have that figured out, I want to think about the direction of my acceleration. So I'm actually going to go ahead and calculate Fg first. And so Fg is going to be mass times gravity, so 1.5 times 9.8, which means that force of gravity there on the hanging box is 14.7 newtons. Since that 14.7 is bigger than this 10 Newton force going the opposite direction, right, if I'm thinking about the external forces on my system, because tension is within the system, that means that this hanging box is going to accelerate down, and that means that the pulley is going to undergo a counterclockwise angular acceleration. So keeping that in mind, I'm going to go ahead and set up my F equals ma for all the forces acting on the box, and my sum of the torques equals I alpha for all the torques acting on the pulley. So on the box, making down the negative direction, I'm going to have Fg minus Ft is equal to ma, and I can fill in some values there, so I know this is 14.7 minus Ft equals 1.5a. I can do the same thing with my torques. I'm going to have the torque of tension minus the torque from that pulling force, that 10 Newton pulling force. And here I'm making the direction of the angular acceleration be positive once again, is equal to I alpha. I can go ahead and make a few substitutions. Mainly, I'm going to substitute in for my torques, do RF sine of theta for each one. And for my moment of inertia, the pulley is going to be a disk, which if you look on your equation sheet in the notes is 1/2 mr squared. So I can go ahead and substitute in for that. So I'm going to have R times the force of tension times sine of 90 minus R times the force of the pull, which is at 10 newtons, also times sine of 90, right? Both of those forces, if we think about the angle between the radius and the force, it's going to be 90 degrees in both cases. And that's going to be equal to 1/2 mr squared. There's actually one last substitution I'm going to make. I know that R alpha equals my linear acceleration, so I can say that my angular acceleration is equal to A divided by R. And what that does is it allows us to link the linear acceleration of the box connected to the rope to the angular acceleration of the wheel, knowing that the rope goes around the outside of the wheel. Its tangential acceleration is going to be equal to the angular acceleration of the wheel times the radius. So I can make that substitution as well. So we're going to put in A over R. And what that does is it allows us to ultimately, when we combine these, solve for that linear acceleration. We can work a little bit with these equations here. Those sines of 90, they're just 1, so they go away. This R here cancels one of those R's there because we have an R on top and R on bottom. And then what we're left with is an R in every single term, and so we can get rid of those. So this equation simplifies down to the force of tension minus that pulling force, which is 10 newtons, is equal to 1/2 the mass. The mass we see is 2 kilograms, so it's just going to be equal to 1 times our linear acceleration. I'm going to solve this equation over here for Ft, and I'm going to say that Ft is going to be equal to 14.7 minus 1.5a. We could also have added those equations, but I'm going to bring these two together, and what that ends up in is 14.7 minus 1.5a. That was that Ft term. Minus 10 equals 1a. So that means that 4.7 equals 2.5 times my linear acceleration. And so that means my linear acceleration has a value of 1.88 meters per second squared. Now that we have that linear acceleration, we ultimately are looking for the time it takes that box to move 30 centimeters. So we can go ahead and set up our regular kinematics. So the distance is going to be 30 centimeters or 0.3 meters. We're starting from rest, it says, so the initial velocity is 0. And that acceleration is the 1.88 meters per second squared that we just solved for. So I can say delta x equals VIT plus 1/2 AT squared. That initial velocity term goes away because it's 0. So I can say 0.3 equals 1/2 times 1.88 t squared, and I end up getting a time here of 0.56 seconds. All right, and there's my answer. It's already to 2 sig figs, so we can just substitute that in. For this last problem here, we have a person sharpening a knife by pushing it on the rim of a grindstone, so just a solid disc. And we want to figure out what force he exerts on the grindstone in order to slow down the wheel at a certain rate. And so first we're going to think about the forces that we have acting on this grindstone. I'm going to do this view from above, so we're going to say gravity is going into the page, normal force or whatever supporting it is going out, and we'll just ignore those and focus on the other forces on the grindstone. So the person's pushing his knife up against the grindstone, so we're going to have a force from that, which is going to be a normal force. And I'll say that the grindstone is rotating like that in the counterclockwise direction, and that means that when the person pushes this knife against the grindstone, there's going to be a force of friction on the edge of the grindstone that's going to ultimately create a torque and slow it down. So we have that force of friction, and that force of friction is going to create a clockwise torque on the grindstone. Now that I have that, I'm going to do sum of the torques equals I alpha. So the only torque I have acting on it is the torque from friction. That normal force is going along with the radius, and so there's not going to be any torque created by that, but there is from that frictional torque. And I'm going to say it's a solid disk here, so that means the moment of inertia is 1/2 mr squared times alpha. So that's the one thing that I'm substituting in. The other thing I can substitute in for is the fact that torque is RF sine of theta, so we're going to plug both of those in. And so I can say that torque from friction is going to be R times the force of friction times sine of 90. I'm also going to put both of these as a negative sign because that torque is going not only in the clockwise direction, but it's opposing my rotation. So I'm going to define clockwise to be negative in this case. So that's equal to 1/2 mr squared alpha. One of those r's cancels out, okay? And I also can substitute in here mu Fn. I know that my coefficient of friction is 0.2, so I'm going to make that substitution here. So this left side is just going to be mu Fn because sine of 90 is 1 and the r canceled out. And that's going to be equal to 1/2 mr alpha. So from here, if I look at this equation, I know mu is 0.2, I know my mass and my radius, what I don't know is alpha, so I'm going to have to go ahead and set up angular kinematics to find that alpha. And so the first thing I'm going to do is I'm going to take this 200 RPMs, 200 rotations per minute, and I'm going to convert it here to radians per second. Okay, and I end up getting an answer here of 20.9 radians per second. So that's my initial angular speed. Okay, I'm told that it drops 10%, loses 10% of its speed. So my final angular speed is just going to be 90% of that. So 20.9 radians per second times 0.9, and that gives me 18.85 radians per second. And so that's going to be my final angular speed here. And that happens over a period of time of 10 seconds. So using that, I can go ahead and solve for my angular acceleration. So I can say 18.85 equals 20.9 plus alpha times 10. When I solve for that angular acceleration, I get an angular acceleration here of negative 0.209 radians per second squared. Now I can go ahead and finish this problem, plugging in all the things I know. So my coefficient of friction is 0.2 times that normal force, which ultimately is what we're solving for, the force that the knife is pushing up against the stone with, and that's going to be equal to 1/2 times my mass, which is 29, times my radius, which I see here my diameter is 0.3 meters, 30 centimeters, and so my radius is going to be 0.15 meters. So I can substitute that in, and then times the angular acceleration I just found, which was 0.209. And when I solve all of that, I get that my normal force here is going to be 2.28 newtons, which rounded to 2 sig figs is just going to be 2.3 newtons.